Good evening for me. It's 7 p.m. in Kansas here. I am Dr. Blair Schneider, and I'm one of the co-chairs for the SEG Women's Network webinar series. And today I am really excited to get to introduce Dr. Elita Li. She joined the Department of Civil and Environmental Engineering at the National University of Singapore as an assistant professor in 2016. Before coming to Singapore, Dr. Li did her postdoctoral research at Massachusetts Institute of Technology, holding a joint position in the Earth Resources Laboratory in the Department of Mathematics. Dr. Li received her PhD and master's degrees in geophysics from Stanford University in 2014 and 2010, respectively, and obtained her bachelor's degree in information and computational science from China University of Petroleum in Beijing in 2008. At the National University of Singapore, Elita's research group works on geophysical applications in urban environments for smart city developments. By integrating ambient noise imaging and distributed sensor networks, the research efforts are focused on the development of a non-invasive, high-resolution, and real-time listening system to solve pressing urban challenges in space, water, and society. Elita was also the recipient of the J. Clarence Karcher Award from SEG in 2018, and the SEG and the SEG South and East Asia Honorary Lecturer for 2022. So if you have questions at the end of the talk, that's not the puppy. If you have questions at the end of the talk, there is a Q&A button at the bottom. So please, at any point throughout the talk, go ahead and put your questions in there. I will also try to keep track of the chat function though, if you put questions in there as well. And if you have any technical questions, just reach out to Shelly on here. And Elita, you're ready to go. Thank you so much.
Okay, thank you so much, Blair, for the very warm introduction and this particularly opportunity for me to share what we have been working on in the urban space in Singapore. So before I jump into the technical details, I would like to acknowledge my collaborators of this material that I'm going to show you today. Li, Gang, and Yumin, they are my team members, postdocs, and students. And Professor Tae-Soo Koo is a collaborator in the Department of NUS, and Dr. Yunhuo Zhang, who was a student in the department and now working with Land Transport Authority in Singapore. And the project that multiple projects that you are going to see are supported by multiple agencies in Singapore, including Economic Development Board, Ministry of Education, and Land Transport Authority. And we were also very lucky to get a support from a private startup company called Cambridge Sensing. So while I was preparing this slide, I was thinking I should give an introduction about Singapore to the audience who may not be sitting in Asia. So I Googled the question, where is Singapore? And this is the map that shows up. So Singapore is a very small island city-state in the Southeast Asia and at the very southern tip of the Malaysia Peninsula. So while I was doing that, I also found out other questions people have asked, such as which country is Singapore in, or is Singapore a part of China? So these are, well, I can answer these questions is that Singapore is a country of itself. It's a city-state. It's a city, but also a country. The capital is itself. It's not part of China. It's not part of Malaysia anymore. It used to be a part of Malaysia, but it was separated and independent from Malaysia about 50 years ago. So I do not, well, although these questions really shows that Singapore is a small country and people have a lot of confusion about Singapore, but I don't particularly blame them because Singapore is small in its size. The total area is only 725 kilometers. That is, in this diamond shape, the direction or the distance across east and west is about 40 kilometers, and the direction from north to south is about 20 kilometers. So it's a very small area. And but within this small area, it's supporting more than 5.6 million people as of 2018, and the number of density or the population density is increasing every year as well. So when we talk about Singapore, it is a very small space and supporting a lot of people. So population density over the past decade has grown from 6,500 to 7,000, around 8,000 people per square kilometer. So, so this is a very dense city. And when we look at the map of Singapore here, when Singapore was first established in 1960s, the land area is only 580 kilometers square. So this is the gray area is where Singapore was established on. And throughout the years, Singapore has been reclaiming its land from the sea. So all these areas in blue and in black are the areas that Singapore has already established previously. That was the sea area, or that was very small island Singapore has built upon. So these are the locations where Singapore trying to increase its water, and it actually increased the land area by about 25% already until today. And the projection of 2030, by 2030, Singapore would reclaim more land from the sea to the red area, but this is pretty much the area that Singapore can, the limit that Singapore can reclaim from the sea. So as you can see, Singapore is really limited from the area that it can grow spatially or in the horizontal direction. And this actually lead to another problem, that is the water problem in Singapore. Although Singapore is a tropical city and there are very heavy storms almost every day, so fresh water actually comes from the sky for free. But Singapore doesn't have enough surface area to host these fresh water to support the need of its urban residents. So Singapore has already done a very good job in terms of turning everything it can use to be surface reservoirs. All these numbered locations are the infrastructures that can host this water, but it's still not sufficient to support the urban demand. So Singapore has to import water and electricity from Malaysia, which are supposed to be the lifeline of the urban life. So the question is, as Singapore wants to develop, as well as all the other very well developed cities in the world, they are limited in the surface area. So what the direction that they are looking at is to going to the subsurface. So Singapore has a very comprehensive underground infrastructure system. From the shallow part, you have the rails, subways, and pedestrian linkways. And deeper, you will have these roads that are cutting across the island without interacting with the surface traffic. And going even deeper, there are utility tunnels and also caverns to store ammunition or petrochemical that Singapore really needs for its energy. So with all these underground infrastructure, what Singapore wants is to free as much surface space as possible so that people can enjoy the sunlight, the breeze, and the green space on the surface. So this is the whole ecosystem of this urban space, where as people move more and more infrastructure into the subsurface, we want to monitor, or we want to see what is going on. So when we try to look for a magic crystal ball to look at to see what is going on in the subsurface, in the end, the tool that we have to use is really, let's listen to what the Earth is doing and figure out what is going on. So let me show you an example of what we have been listening in Singapore. So this is a road at the NUS, the university campus at the exit. And we have students holding a smartphone camera pointing at the road. So you will hear the traffic coming in and out. And at the same location here, well, it's not in the picture, but there is a seismometer that we have installed right by the road at the location as well. So I'm going to play the video so that you get a sense about what the sound that you will hear every day in urban space. They are very familiar to you, but I will just dissect it as we are going through the video. So let me play it. So at the beginning of the video, we hear a lot of wind, and we also see the wind coming in. Then the motor pipe comes in, but we do not hear it until it turns around the corner. There's a car. And another car going at the opposite direction of the road. We don't hear it, but we see it from the video. There's another car coming by. One more car. A little truck. Another car going in the opposite direction. And at the end of the video, I hope, although we don't see it, but I hope you hear the sound. It's actually a sound of an airplane on top of the very strong wind. So this very large audio signal that is coming from the airplane can be recorded by the audio signal or by the cell phone. So as I said, there is on top of the audio or the cell phone recording, we actually have a seismometer installed at the same location. It's a 3-component seismometer that you probably are very familiar with. The way we installed it is the N component is parallel to the road, measuring the vibrations in the horizontal direction. The E component is horizontal but perpendicular to the road, so it's coming in and out of the road surface. The Z component is up and down. It is the vertical motion that is caused by the ambient vibrations. So if you compare the vibration or the ambient noise sensed by the seismometers with the noise sensed by an acoustic sensor, a microphone, you can see there are very strong similarities between these. But clearly, we are not as much affected by the wind. The very large wind noise is not recorded. And it seems that we are not recording the airplane information as well. This part of the vibration is very, very weak. So we decide to take these signals into a different domain and take a closer look at it. So this is the spectrogram that you will see over and over again. This is the primary tool that we turn a time series that happens in time into a time frequency domain signal that it becomes a picture and we can visually identify events from that. So the vertical axis here is the frequency each of the signal presents. And then the horizontal axis shows you when this signal arrives. And this is a recording about half a minute long. And this is the recording of the microphone, so the acoustic sound. And from the video, remember we marked out all the events that was happening during this video recording. And it was, by the way, the color here really shows how much energy shows up at that particular frequency and at that particular time. So when we look at this time frequency analysis with the event or with the actual video recording, it's very difficult for us to identify individual activities because the noise or the acoustic signal is overwhelmed by this background wind noise. So all of these frequencies are showing very, very high energy. But at some locations, say when the truck goes by, we started to see a strong energy going across the whole frequency domain. And one last very dominant feature on this panel is the airplane signal. It corresponds to this feature where frequency changes as a function of time. So this is a Doppler effect that we would hear and we would record using the microphone. And so if we compare this microphone recording, oh, by the way, another feature I want to point out is that the low frequency component of the audio recording is actually very weak. For everything below 20 hertz, there's almost no energy. And this is because human ears has a hearing frequency range from 20 hertz to 20 kilohertz. So everything below 20 hertz, we have very little ability to hear. So that's why all these hardwares on our cell phones have a filter below 20 hertz. That means we don't have to record them if we don't hear them. So if we compare these microphone recordings with the seismometer recording, now I'm only showing the Z component, you are going to see similar but different characteristics. So one of the first difference is that we actually start to see strong, very strong and constant low frequency signal from 0 to 25 hertz. So this is a very constant, because it goes across the whole time axis, a very constant energy that is happening in the city. And this is caused by the traffic that is going on from all directions and from all locations all the time. And whereas when there is a traffic or a vehicle directly arriving at the receiver, we are seeing these very direct and very broadband response on the time frequency analysis spectrum, on the spectrogram. So from this, we can see that we can count directly how many vehicles has passed by directly next to our sensor. So when the car is going on the other direction, for example, this one, on the spectrogram, we don't see a signature that we would see if the car is passing by very closely to the seismometer. So the comparison of this car that is just maybe 10 meters away and another car that is very close to our sensor would tell us how attenuative near surface is. The pavement itself and the near surface structure has removed most of these high frequency energies that we see with a car in the lane close to us. And that leaves the low frequency information propagating through the subsurface. And lastly, I want to point it out is that although on the time domain signal, we thought the airplane signal was not recorded, but it is very clear in the spectrogram that the airplane signal is recorded. And it's actually showing a lot more clearer, a much clearer signature of the Doppler effect that we just saw compared to the acoustic sound that I just showed you. So with this, what we can extract from this piece of noise, vibration-induced noise, is that we can, at the low frequencies, we can use these seismic waves from far-field traffic and use these information to use this seismic waves or vibration to invert for the subsurface information. And then at these high frequencies, we know these are direct loading of motor vehicles, so we can use these to interpret what is going on in this urban space. And lastly, we also have this air-coupled engine sound, and this will tell us what is happening above the surface, above the space that we immediately touch upon. So these are very useful information. And limited by the time of the talk today, I'm going to focus on the first two elements of the data, so low frequency part of the seismic wave and the direct loading of motor vehicles. So as geophysicists, of course, we don't have a single sensor. We actually have an array of sensors. So with the recording that you saw, we actually have 12 sensors installed. And these are smart solo sensors. They are individually installed and distributed along this road. So one thing I want to point out is this is a university road. It's relatively small, but just outside it is intersecting a major road. It's called Clementi Road. The traffic here is very heavy, and we see a lot of faster and heavier trucks going on Clementi Road as well. So when we put the array sense data together, we started to see a lot more information. For example, we see some trend of energy going across the array at a speed that we can estimate. And there are other things going on here as well. So if we take a closer look and band pass this array data to different frequency bands. Now, the right-hand side, I'm showing you the Z component data between 75 Hertz and 300 Hertz. So clearly, the trace you were seeing just now is somewhere in the middle, around 70 meters distance. So this is the trace that we were seeing where 4 cars or 4 motor vehicles can be clearly identified. When you put the array signal together, you not only identify the vehicle, but you can track it. So this would be one of the motor vehicles, another one. And because there is a corner that the traffic has, where there's an intersection at this location, so we can actually tell that this truck didn't come from along the road, but it actually turned a corner from that location. So these are the information that we can extract. We identified 4 vehicles in 30 seconds, and we can also calculate average car speed, which is 36 kilometers per hour. This is below the speed limit of the university, which is 40 kilometers per hour. And if I put it in seismic terms, it would be 10 meters per second. It's very, very slow. But if we look at the low frequency part, this is between 0 and 25 Hertz. So although you also see this slanted low speed wave or low speed recordings, but there are more of the waves that is showing a very faster, much faster velocity, and that it seems coming from the other direction. So instead of coming from the traffic direction, it is opposite to the traffic direction and traveling at a much faster speed, which is around 200 meters per second. And this is, in fact, the seismic wave or surface wave induced by the traffic on Clementi Road. And those waves propagate across the array at a much faster speed. So we will use these surface wave or seismic wave information to invert for the subsurface activities, and then use the surface wave, the high frequency information to invert for surface activities. So let me show you a few examples here about how we extract rich information in the urban space. So for the subsurface information, one primary target is bedrock in cities. So I'm going to show you 2 examples where we need to identify or find out where the deep bedrock is to constrain a deep freshwater aquifer and estimate how much volume that we can host in this freshwater aquifer for Singapore. And secondly, I will show you a shallow bedrock application for which has very high resolution requirement for tunnel construction. And then I will show you another application for urban activity monitoring during COVID-19 and show you that with these vibrations, we can extract a lot of information about traffic and pedestrian without having to worry about privacy intrusion. So this is a bit background about Singapore. Again, the geological condition here. Singapore, this diamond shape can be divided into three parts. In the center, it is the igneous rock. It is called Bukit Timah granite. It is actually all the way to the surface. And then to the east part of Singapore, this Bukit Timah granite, there is a fault, a major fault in Singapore. So Bukit Timah granite is subsided, and on top of it, this sediments was deposited on top of the Bukit Timah granite. So the idea or the conceptual model based on outcrops is that because there are granite intruding on the surface, people have thought that the bedrock of granite is dipping from the northeast to the southwest. So that it creates a wedge of the sedimentary columns. So we can use these engineeringly, these sedimentary columns may be used as deep aquifer so that the surface water that cannot be stored fully can be injected into the subsurface and stored there. When it's needed, then these fresh water will be extracted out and recharged during the rainy season. So our goal of the seismic acquisition is to figure out how deep this Bukit Timah granite bedrock is, so that we will be able to estimate the volume, the total pore volume of these sedimentary column, and then how much fresh water we can store. So in order to answer this question, most of the uncertainty is actually on the east part of Singapore. With all the outcrops of Bukit Timah granite, we want to know how deep the bedrock are in this area so that we can extract information about the total volume. So I'm going to show you one particular site, which is from the north shore of Singapore at the top star location. So this is a beach site, and we have ocean waves coming from the north, hitting the shore at the frequency about once per second, 1 hertz, or 2 hertz when it is very stormy. And then we have all the urban life happening in the south of the park. So the red dashed line is the geophone array that we have laid out along a park road. And there is a borehole location not too far, about 300 meters away from our geophone array. So this is the data that we report. The total recording length is about 3 hours. So the student would deploy the sensors and sit there and listen to the ambient noise. So when you look at each single trace, it's very, very noisy, but when you look across the trace, there are a lot of coherent events that we can use to extract the subsurface information. So we use the first, the receiver, the northeast receiver as a master trace and perform cross correlation and seismic interferometry that is basically cross-correlating the first trace with all the other traces and adding 3 hours data into a short segment about 4 seconds. So this is the cross-correlation result. And let me remind you, to the north of the array, we have the ocean waves hitting the shore, and from the south of the array, we have all the urban activities like traffic, construction, and so on. So what we saw here is that the interferometry result shows very strong directionality. So from the south to the north, we observe a very high frequency and high speed wave coming from the city. So if we take this part of the wave, do the phase velocity analysis, we actually see that the frequency is much higher compared to normal ambient noise that we would report. And the velocity is very high as well. It actually goes around 2,000 meters at high frequencies and goes all the way to about 5,000 meters per second at lower frequencies. So this although seismic interferometry has been performed for say earthquake seismology and large-scale low-frequency ambient noise in the earth, this kind of high-frequency and dispersive waves are rarely observed. So when we look at the other side of the signal, we see a much lower velocity signal, lower frequency as well, and much more dispersive compared to the waves coming to the other side. So if we take this part of the wave, the positive time lag coming from the ocean, and perform the phase velocity analysis, what we get is a normally what we would see using ambient noise is that a very low velocity that is around 150 meter per second, and it goes about 600 meter per second at low frequencies. So these are the signals that we can use to invert for the subsurface structure. And the way we use it is, in this case, we identify this as Rayleigh waves, the surface Rayleigh wave. And this, we identify it as a guided P wave that is trapped in the shallowest layer between the sediment, in the sediment column, and the deeper layer is the Bukit-Timah granite. So we jointly invert these two phase velocity dispersion curve, and we will be able to extract a structure in terms of both shear wave velocity. This is what people would usually see for the ambient noise imaging. And on top of that, we are also able to extract the P wave velocity from the P guided wave dispersion. And so when we get this shear wave profile, we will be able to interpret them according to the geological and information. So they are separated into organic layers, sediment layers, and the last layer would be the Bukit-Timah bedrock. So if we compare our seismic inversion result with the borehole log that geotechnical engineers have obtained previously, they have a good agreement, usually with a very, very small or very low speed sand layer on top and some sedimentary layer in the middle, and the color, dark red color here is the granite. So if we look at the bedrock depth from seismic noise, we identify it at around 103 meters, where there is a big shear wave jump, shear wave velocity increase. And the bedrock depth from the borehole log is about 115 meters at this location. So we think this accuracy is very, very satisfying. And we actually repeated the exercise in many locations, 7 different locations across the area, and we were able to compare the bedrock depths from boreholes with the bedrock depths estimated from seismic noise. So in order to achieve this, what we need to do is very simple, and we did not put in additional energy source in the subsurface. We were just listening to the traffic noise, to the construction noise. Whereas when you sink a borehole, although this information may be more accurate and more concrete, but it takes a longer time, usually up to a week, and a lot more energy. So when we compare these two, at some locations they agree with each other very well. At other locations, they are not agreeing very well with each other. There are many reasons. One of them could be due to the variability of ambient noise. And so in this case, I think what we want to conclude is that based on seismic noise, we actually see the bedrock depth is much deeper than just intruding on the surface, and it's also confirmed with the borehole data as well. So this actually leads to an updated conceptual geological model. Instead of having the bedrock intruding into the surface on the east side of Singapore, we believe there could be another small-scale fault that actually make the bedrock as deep as 100 meters to the east side of Singapore, and it's dipping to the southwest. So the result of this updated conceptual model has the potential to increase the aquifer storage volume in the sedimentary column. But on the other hand, because of the existence of this small-scale fault, we also need to worry about potential leakage pathway because of the fractured granite bedrock. But in this case, we are very happy that by harvesting the low-frequency noise, we are able to provide such a geological interpretation. So let me show you another example where we need to identify the shallow bedrock for tunnel construction. So let's move to the west part of Singapore. The east two sections are very close to each other, and they belong to the same tectonic history evolution. But the west part of Singapore is something called Jurong Formation. The age of this Jurong Formation is the same as Bukit Timah granite, and it's a sedimentary rock layer. It has been very heavily folded, and a lot of the structures are thrusted and eroded by the environment as well. So when you look at an outcrop here, you see different sections just 1 meter across having very different color and showing very different strength as well. So as the tunnel team goes underground with subway tunnels and so on, these soil rock interface or hard and soft rock interface has posed a lot of challenge to the tunneling team. So what they want to do is to identify or to extract information about these near vertical faults that may have a very small throw, but that has very strong property difference between each other. So what we have done is we put a seismic section, a few locations to the west part of Singapore, and this is on the campus of our brother university called Nanyang Technological University. And we chose this site because there are 4 boreholes at this site, borehole 1, 2, 3, and 4. The bedrock depths defined by geotech engineers or civil engineers are very different just across the road. So the bedrock is much deeper at 34 meters on the left-hand side of the road, and they are much shallower, 20 meters shallower at borehole 2. And the bedrock depth actually increases to 27 meters to borehole 4. So we want to figure out what is going on across the borehole and how does the bedrock dip in this area. So we placed seismic stations and recorded background noise. And the stations, there are 8 receivers connecting borehole 2 and 3 with 4 meter spacing, and another 10 receivers connecting borehole 3 and 4. So we went out and listened to the ambient noise again for about a few hours. Then what we get is the data that we record from number 2 to 19, these are recorded on the same day. And we actually went out on a different day and recorded a different set of noise at borehole 1. So traditional seismic interferometry actually requires us to listen at the same time so that the noise can be cross-correlated. But in this case, we need higher resolution. That is to say, we cannot really average across the sensor array, and we have data recorded on different days. So how do we make use of those? So the way we process it is inspired by a statement by John Claerbout. He said, by autocorrelating the data, ambient noise, we can convert these noise into something that might be the impulse response of the Earth. So this is a very vague statement So what we take away from it is that using autocorrelation is effectively collapsing the seismic acquisition into a zero offset experiment, and that is virtually a sonar experiment. And with this concept, what we can do is really increase the resolution such that the average across the array is not needed. And we will be able to utilize the noise recorded at different times because it only involves autocorrelation instead of cross-correlation. And so this is a chance for us to achieve super resolution, so to speak, with respect to the surface wave and body wavelength. So this is what we did. The right-hand side shows you the autocorrelation image that is calibrated using two of the boreholes. So in this case, we're using borehole 2 and 3, and did autocorrelation actually with a deconvolution in it. So we will be able to identify the strongest reflector in the autocorrelation, and that is the bedrock that we are looking for. So the star location is the bedrock that we identified on the autocorrelation time data, and using a calibrated p-wave velocity of 15 meters per second, we can convert that time data into a depth data. So all the star location is the bedrock depth that we identify from ambient noise. And what we see is that on the right-hand side of the road, we have the bedrock is dipping to the east side, and there is a small throw or small scale fault just right after borehole 3. And then the throw of the fault is about 5 meters. So we also use the same technique to process the data on a different day for borehole 1. And as you can see, the actual borehole depth based on borehole agrees very well with the mapping from the autocorrelation method that we have used. So this is a good success that we believe we will be able to utilize these very short recordings at high frequencies to map out bedrock depths at a very high resolution. The spacing is 4 meters, so in theory, we have resolved a small scale fault just across 4 meters distance. And lastly, since I've shown you the subsurface applications, let me show you another one for the above surface urban activity monitoring. And well, we have all lived in the past 2 years during COVID-19 lockdowns. So I will show you what is happening here as geophysicists, what we can do. So one of the most famous or well-known studies in seismology for urban monitoring is probably this study published last year by a whole team of seismologists across the world. So each of these locations is a seismometer, and as the whole world goes into lockdown, we started to see all these seismometers they are showing a quieting down or a lower energy at the low frequency band that is around below 14 hertz. So this is the area where most of the world has went into lockdown. And what we want to do is in Singapore to have a relatively high frequency understanding or high resolution understanding about at each location what is going on, because the urban space is so heterogeneous, and what happens here could be very different from what happens a kilometers away. So we have 4 different sensors installed, one at NUS exit, the location that you have seen before, one at the hilltop of NUS where the activity is very, very low. Then another one at the highway location. So this is West Coast Highway. It connects the island on its outskirts. So a lot of heavy trucks and all the utilities that it has to be transported across the island are going on this road. And lastly, this is a location at the intersection between the Pasapanjang port terminal. This is a container port terminal with a park. So this location will tell us about the recreational activity and also the activity going on between this international port terminal and also the island state of Singapore. Because Singapore doesn't produce anything, during lockdown, we still need the international supplies to come in to support our very basic life and medical needs. So this is the urban noise heard by seismometers. So what we see are, these are the PSD, power spectral density, at 4 different locations. Of course, the highway location has the largest energy because it sees most of the traffic. The park and the port and NUS exit has similar level of energy, but at the port, because there are more trucks, we see a lot more low frequencies compared to the NUS exit. And the weakest or the most quiet place is on the hilltop of NUS. So what we are focusing on is these high frequency energy that really reflects what the activity locally. So we have seen this similar picture before. We can identify the traffic, the motor vehicles, from the high frequency vibrations in the Z component, and we call this direct loading. And the way we do it is really just look at the energy or the average energy at high frequencies about 50 Hertz. And then this red dashed line will give us peaks, and these peaks would denote the location of or the time for the traffic to arrive. So the characteristic of direct loading traffic is that they are very strong impulsive energy sources, and they have a very broadband response from 2 Hertz up to 350, and for larger vehicles, it's up to 450 Hertz. And the heavier vehicle will give us larger energy and broader band. So this is one type of the activity. Another type is pedestrian. So when we look at the high frequency signal in a very clear day, is that this is the time domain signal filtered between 40 and 100 Hertz. So you see 3 groups of energy, and they shows up very differently. These two, as what we have understand, are from motor vehicles, and this one showing a cone shape or a fishbone shape. This is actually pedestrian with each spike a footstep that the seismometer has recorded. So what we have done is we can look into the envelope of the spectrogram and do a spectrum of the envelope function, and for the ambient noise and also the traffic noise part, we do not see strong characteristics, but for the footstep signal, we see strong characteristic of harmonics, and these harmonic have specific frequency, primary frequency range that corresponds to how many steps we usually take while we walk or while we run. So these are the characteristics of pedestrian signal. They are usually long durations. They are 20 seconds long, but their energy can be very low. And they are most obvious at high frequencies. And their spike frequency, which can be converted to cadence, is between 100 and 200 steps per minute. So we use this information to process the data that we recorded for 4 months during COVID-19 period. And these are the results. On the horizontal axis, these are the calendar days in 2020. And on the vertical axis, you have the daily hour converted to local hours. So CB is called circuit breaker. It's a total island-wide lockdown for Singapore. And during this period, the color scale here shows how many motor vehicles that we have identified from the seismometer data. And what you see is that during the lockdown, the traffic activity is very low at NUS exit. And starting from early June, Singapore comes into phase 1 and phase 2 opening. So what you see is the traffic volume in terms of the vehicle count number grows. And gradually you get back to this feature that we are very familiar with, rush hours in the morning and another rush hour in the evening. So if we plot this, the number of motor vehicles on each day and compare it, which is the blue bar, that is our data, compare it with the Google mobility report, that is the black dashed line at workplaces, we see there is a very good agreement between our data and the Google mobility data. But this is completely anonymous. Our data is completely anonymous, and we don't need intrude into privacy. And we can also average or statistically look at the data for the weeks before lockdown or after lockdown, or the weeks in the lockdown. So what we see is after opening, after the lockdown, the traffic volume jumps about 30% or 50% at other locations, and the peak hour phenomenon comes back. And during weekends, the traffic jump a little bit, not as much as the weekdays, and also there's no peak hour as we observe. So this really shows that as a non-essential workplace at NUS, the traffic data shows that people have shown great compliance to government mitigation policy. So during lockdown, the traffic volume is really, really small. And as a result, community transmission of COVID-19 was about fully eliminated towards August. But now we're having second wave or third wave during the other variant, but that is a different story. So when we compare the traffic activity at the NUS with the activity at the port, we see quite different phenomenon. One significant thing to notice is that during lockdown at the port terminal, the traffic is not reduced at all. Actually, the traffic increased a little bit towards the second half of the lockdown. So now if we compare the Google mobility report for workplace percentage change, we can see that our estimation is much, much bigger compared to the Google data. And when we compare it before opening and after opening, the difference is very, very small. There is a bit of increase, but it's less than 5%. So this is really telling me, actually, the terminal port is an essential workplace. And because Singapore has the need to bring in all these essential supplies from the port, it was open despite the restrictions of the government. And these are really the lifeline. The essential service load actually increased during the second half of the lockdown. And this shows that because we are relying on the international supply chain, so the data and our experience shows that this supply chain survived under the extreme stress test of COVID-19. So let me use the last few minutes to show you the data for runner activities at the park. So this, again, is daily and hourly runner count at the park. So what we observe is that Singaporeans actually wanted to run much more in the evening compared to the morning. And of course, in the middle of the day, there's almost no runners because this is a tropical city. It's very, very hot during the day. And another observation is that after opening, the evening runners actually reduced its number, although the morning runners kept at a similar level. And with our data, we can actually analyze the cadence of each runner as well. So we can analyze the performance of morning runners compared to evening runners. So what we have learned is that if you are a professional athlete, your average cadence is around 180 steps per minute. So the red bar is where you would be a good runner compared to a lower cadence would be a slower runner. So what we see is that in the morning there are more faster runners compared to in the evening, and the morning runners are more disciplined. They are not as affected by the lockdown restrictions, whereas the evening runners numbers are greatly reduced after opening. So at this location, and we also conclude that the lockdown itself actually promoted evening workouts, especially during weekends. And after the opening, we see a dramatic decrease in Sunday evening runners. And this indicates that when people need to get back to this daily or weekly routine, people started to shift their workout habits. So let me wrap up what I've shown you today. What we really want to do is to do geophysics for a smart, sustainable, and resilient city. And I think this is needed not only for Singapore, but also for many other cities like Beijing, Shanghai, and say Manhattan, these cities where infrastructures are very well developed and a lot more monitoring is needed. So I've shown you 3 applications, deep bedrock mapping, shallow bedrock mapping, and also urban activity that is happening on the surface. So the detection depth is increasing or actually decreasing, and the time needed for this detection are also decreasing. So this is the goal. The goal we want to achieve is to use the ambient noise that is happening all the time for real-time monitoring, and this real-time can be relative to the need, but we would like to contribute to the urban monitoring and urban management. So what I want to conclude is on this slide, we want to do geophysics in cities, and we can participate in all the stages. During the planning stage, we can help with site investigation. During the construction stage, we can do monitoring and to help for engineering management and safety. And during the operational stage, we can actually monitor the health of the infrastructure itself, or monitor how the infrastructure is used, and provide guidance for preventive maintenance. So with that, I'm gonna end my talk, and I hope to inspire more discussions in the urban space and welcome any questions you may have.
Thank you so much. So I have not seen a presentation that connects geophysics so well with something like COVID. That was really interesting.
Yeah.
I wasn't expecting it, and I was just really cool. And I have a quick question. Have you found any sources of ambient noise that end up being more problematic than helpful, or has it all been useful?
Yeah, of course, depending, well, one's poisonous, the other's candy, right? So depending on the applications, say for example, when we want to use the seismic or surface waves for interferometry, we actually wanted to eliminate the direct impact of cars, because that is a very strong source. So we have to do this noise source separation to really separate the sources from each other, so that for one application the data is clean. Yes, this is also, I think, we are driving towards an area where we can use machine learning to separate all these sources, and then afterwards each data type is used individually just for its own purposes.
That is just very, very cool. A question from Anna: how do you get the civil engineers to listen to you, and how do you make them understand what you can do?
Yeah, that's a very good question. I think I have an advantage because I'm sitting in the civil and environmental engineering department, And I have a few very open-minded colleagues in the department, and they actually came to me with their needs. Say, for example, when they want to figure out how deep the bedrock is, it's not common for civil engineers to drill a borehole that is 100 meters deep. Because for infrastructures, they usually would just drill maybe 10 meters, 20 meters, maybe up to 30 meters in order to reach a rock that is strong enough to support the infrastructure. But for the very deep bedrock that goes to 100 and 200 meters, it would cost them a lot to drill those deep boreholes. So they actually want geophysicists to help in this domain. And also for tunnel construction as well, I think engineers are becoming more and more aware of the limitations of these point boreholes. And because of the variability and heterogeneity of the geological condition, they also want to figure out what is in between. Oftentimes, the boreholes are about 25 meters or 30 meters apart from each other, but as I said, as I shown in the pictures, the geology can vary on the order of meters. So they want to know what is going on in between, and that I think that is an excellent place where geophysical methods can go in and calibrated with these boreholes. We can provide a lot more information at a higher resolution, and both us and the engineers need for construction.
Yeah. So you're collecting data in a really busy area. Do you have any like additional considerations or things that you have to take into place in terms of just dealing with like people walking around or messing with equipment? I'm just thinking of all of the citizens that would just be walking up like, what are you doing?
Yeah, it's a very interesting point, and I think there's a cultural element to it as well. And we are so surprised. We put these smart solar nodes at individual locations. I think people, citizens in Singapore, they are curious. So while we are putting the sensors, they would stop by and stand there and look at us. Or some of them would ask what we were doing, but just from the data, we really don't see people messing around with our sensors. And because we place the sensors out there for months long at a time, none of the sensors were missing. So Singapore is very, very safe. We don't worry about sensors got stolen or people were too curious and play with our sensors and so on. So I guess we are lucky in this way. But the unlucky aspect is that so when my students and postdocs went out to the parks for acquisition, they need to watch out for the mosquitoes. They are really prevalent in Singapore, and they can be attacking quite vigorously. So those are the things that we have to look out for.
Well, this has been a super interesting project. For the sake of time, I'll go ahead and wrap things up, but this is recorded. This will be available on the SCG websites, so individuals can go view afterwards. And I just thank you again. Such an interesting talk. You're doing some really interesting research. I'm really glad we got you on here.
Right. I guess this is showing, I hope this shows that as geophysicists, we can do a lot more than just looking at underground and get closer to society, closer to everyday life. And I hope this inspires people to participate in this area.
Yes, absolutely.